let's look at the details of what happened when that wire burst into flames. We decided to apply delta V to a conductor. And clearly, somebody was not happy about it. So let's imagine, let's sort of zoom in on that, a piece of that wire. Draw it kind of like this. So it was a conductor, and it was a cylinder. And that's what we did. We attached it to a battery, so we forced this side to be at 0 volts, and we forced this side to be at 12 volts, based on our definition of the negative terminal being 0 volts. And what's going to happen? Well, we know that this is similar to when we talked about a conductor before. If you put it in an electric field, you have some E applied. An applied electric field from the positive to the negative terminal. And this was the E, sort of like the one that's between the battery terminals. Okay? When you apply that to a conductor, we know what's going to happen. If there's negative charges in the conductor, and in this case the free charges were negative, they were electrons, little negative electrons, they're going to feel a force that's going to make them want to move this way. So all the little electrons that are negative start to drift that way. And if you want to think about it this way, there's also little missing electrons. Sometimes we call them holes, although in a metal they aren't as important. But since they're positively charged, they feel a force that way. So the charges start to drift. Positive to the right, negative to the left. But then here's the difference, is because of the battery, the charges do not build on the ends. When the charges get here, they don't build up, they just fall into the battery. Okay. That's how it's physically different from sticking the conductor in just a uniform electric field. Now we're touching it to a battery. And at the battery terminals, chemistry wants to happen. And the electrons say, I'm not just going to sit here, I'm going to go complete the chemical reaction in the battery. Same thing happens here. The positive charges of the lack of electrons contribute to the battery. That's how the battery maintains a constant potential. So if the charges can't build up on the surfaces, no opposing field is created. There's nothing to make things want to stop. They just keep going. No opposing field is created. E applied, APP, exists inside the metal. Completely the opposite of what we learned about before. Before we said if you put this in just a uniform electric field, charges will move, E field will go to 0. Now we're saying that doesn't happen because the charges can't build up and create an electric field. You'll still have a potential drop. Since we have an E applied, there's the 11 volt line, and the 10, and the 9, and the 8, 7, 6, 5, you get the idea, 4, 3, 2, 1, down to 0. So this face is at 12, this is at 0, and the potential drops throughout the metal. And then finally, what you end up with then is you have a continuous flow of charge, which I'm down to the most important part, what we're trying to get to. I'm going to put it right here in this teeny little part right here, which is current. Current is a continuous flow of charge when you're not in electrostatic equilibrium. That's the reason this is different, is we're not in equilibrium here. That's why you can have an electric field, you can have a potential drop, and the result is that current flows. Charges flow in the form of a current.